Okay, so let's do some review of what we talked about before our week off. If you guys have the notes for today in front of you, if you've even perused through them at all, they're mostly a lot of pictures. Like, I know there's quite a few pages there, but I mean, yeah, there's some written stuff, but there's no blank slides where I've got work for us to do. So today's notes, the new stuff is not overly, I wouldn't say it's overly challenging. It's a lot of diagrams, a lot of graphs if you look at this. So why don't we spend the first while though? Let's do some review of the main topics that we covered before we left. So, and I've got actually a diploma question that kind of covers each of the 5 topics we did. So, first topic we did was very first day of school, and honestly it was very basic. I need you guys to know the 3 main kinds of reactions that you're expected to have memorized. One is photosynthesis. The second one is the opposite of photosynthesis, which is cellular respiration. And the third one is just need to know in general how combustion works. Does that make sense? And along with those 3 things, another outcome is that you have to know where the source of all energy comes from. Which, I mean, I mockingly make fun of people who get this wrong because people get it wrong on the diploma, but it is the sun. Okay? The sun is basically the source of all of the energy we have. If you want to consider the breakfast you ate this morning, if you ate Cheerios, it's based on, I don't know, there's whole grains and wheats and oats there. Those are plants. Plants come because they were grown from photosynthesis to the sun. Okay? Energy you had in your car to get to school this morning comes from gasoline. Gasoline is refined from crude oil, which is built up due to lots of pressure and high temperatures over thousands, millions, I don't know what the number is, but over years and years and years because of what we believe was dead plants and animals during, like, say, dinosaur eras. Does that make sense? I know I'm simplifying it a lot, but those plants and animals, though, would have lived because of, again, the sun. Fair enough? So that was pretty much topic 1. Like, it was very, very straightforward. So let's try a question that is off of an old diploma. See if you guys can answer it. So why don't I give you a minute or 2 just to kind of read it through, maybe write down what you think your answer is, and then we'll talk through it. Hopefully I've given you questions like this before in Chem 20 that were structured kind of like this, where I know it's numeric response, but really this is a fancy fill in the blank, isn't it? Right? Like, that's its goal. And I can't guarantee that it'll always work like this, but chances are the first bullet is going to be either 1 or 2, the second one's going to be 3 or 4, the third one's going to be 5 or 6, and the last one's going to be 7 or 8. And that's probably how it's going to work. Please don't default to that, but that seems like the most likely possibility. You want a chance to read it over? Okay, let's talk it through then. Photosynthesis, do you need solar or heat energy? Yeah, we're talking solar energy on this particular one. That's a good distractor, though. I mean, our whole unit's been about heat, but it is solar energy from the sun that we need, light. The next one's kind of mean because it requires your knowledge of words that are actually not Chem 30, but it's actually Chem 20. It's an intramolecular bond that gets rearranged. Do you guys know the difference between intra and intermolecular bonds? Here, let's just make some models again. I know some of you it's only been a couple of, like maybe a month or so. Some of you it's been a long time. Here's 2 molecules. If they were a solid or a liquid, these molecules would get stuck together like this, and that would be an intermolecular bond. This bond right here, any of those bonds, are known as intramolecular bonds. Intermolecular bonds are what makes things solid, liquids, and gas, and so that would be like a phase change. If you melted something, it's an intermolecular bond you're breaking. An intramolecular bond is if I actually rearranged this stuff, and whenever you're talking about a chemical reaction, you're breaking the internal bonds. Does that make sense? So intranuclear, I guess maybe you wouldn't think to pick that because we don't really talk about nuclear reactions in this course, but in previous chemistry courses they actually talked about nuclear reactions, which is more of a physics thing nowadays. So 4 should be the next one. Do you think this increases your potential or kinetic energy? Potential, yeah, because it's photosynthesis, right? What is that? It's a stored form of energy. You're forming your glucose, which is going to hopefully be used again in the future. And then the last one here, it says cellular respiration or combustion. They are exothermic reactions. Does that work? So that's kind of a nifty question design that really kind of covers our first day's topics. Do you know the three main reactions? And do you understand the basic concept of where energy comes from? So that was day one. So far, so good? Okay, our second day was a very mathematical day. Before I show you the question on it, let me just give you like an example of what we worked on. We worked on slowly but surely putting together a very convoluted formula that looks like a combination of this. Q equals mc delta T, which is your basic calorimeter equation, but then also recognizing that Q is really like a form of, we sometimes call it a delta H, an enthalpy change. And I should have really written it a little further over here, but that could be the same thing as a delta H per mole times by how many moles you have. You're kind of putting all of that stuff together in one big equation. And you may or may not even have to use all of that information. Does that ring a bell, kind of using that sort of concept? Okay, well, let me show you an example of a question then. And this is a very typical question. I would put this on my list of must-knows. They give one that looks like this almost every year. So I'll give you a few more minutes to look this one over because you got to do some math as well. Now, by the way, this doesn't require the mc delta T, by the way, part of the equation, but it does involve some calculations that are kind of in that similar concept, where you've got to find a way to turn grams into megajoules somehow.
Lane Light, please come to the office, Lane Light.
Thanks, Bird. All right. I don't wish to be mean, but you need to be done in about the next 30 seconds. And that's not based on my time limit, but it's based on what I need to start helping you guys work toward, which is the diploma time limit. Have I told you guys how long you get per question on average? Okay. You're given 60 questions on the Chem diploma. It is the longest of all the diplomas. For any of you guys who wrote them before, math is 40 questions, physics is 50, chem is 60. You get 3 hours. So based on that math, you need to be able to answer a question on average in less than 3 minutes. So you've got to be able to fly. It's one of the biggest reasons why I'm quite harsh in my Chem 20 in terms of my expectations of you need to be able to find a molar mass, and you need to know these terminologies. You have to know that stuff, like without looking it up. Because if you can't find the molar mass of C2H2 in 20 seconds or less, you're taking too long. Does that make sense? Like, I don't mean for this to be like I'm going to kick you out sort of thing, but if you know that you're slow at that, you've got to get faster because you got 60 questions to do in 3 hours. Like I said, it's fast. So, okay. So everyone had chance to at least try it. Okay, where should you start? Which number is a good starting point number? Yeah, you're right. The 100 grams is a really good place to start. So I would do this, especially if you remember how I try to show you to do stoichiometry. Is grams a particularly useful measurement in chemistry? We can measure grams because we have a scale, but usually we prefer to work with moles. So that's why I was pointing out, you gotta be fluent in knowing how to do a molar mass. Right? I mean, I'm not saying you have to have the whole table memorized, but 1201 times 2 plus 101 times 2, I got 2604. So that's great, we got to moles. What we really need now is to find a way to get like a kilojoules or a joules, so some sort of joules number per mole. I'm going to do kilojoules per mole to start with, because that's at least we're getting closer. Do I have a kilojoules per number listed? Well, kind of. Here's a kilojoules number. So I guess I could say that there's like the 2511 right there. But is that per 1 mole? Well, for 2 moles, it really depends on who we're talking about. If it was water, it's per 2. If it's carbon dioxide, it's 4. If it's oxygen, it's 2. But since we were talking about this guy right here, C2H2, which is acetylene, by the way, there's a 2 written right here, so it's that many kilojoules in 2 moles. You could actually divide it by 2 if you like, or I'm just going to write it out as the 2511 divided by 2 right there. Does that make sense? So now you just need your calculator. 100 divided by that molar mass of 2604, and times by the 2511 they list for you, but divided by 2 because there's 2 moles showing, and I get 4821, something like that. Why is that not going to work though? Well, it's in megajoules, so hopefully you're fairly fluent in knowing your conversions. There's just regular joules. 1,000 of those makes it a kilojoule. 1,000 of those makes it a megajoule. Long story short, divide by 1,000, you need 4.82 megajoules. Anybody get that? Okay. You need to be able to get that soon. Okay, like that is a guaranteed. They're going to ask you that question, and if they're going to ask you that question, I'm going to ask you that tomorrow on your quiz issue. Okay. Once you've seen it before, it's hopefully not that bad. Does it not? For even my grade 11 kids right now, does it not kind of remind you of stoichiometry from last semester? Like it really at its core, that's what it is. That's why I kind of beat the crap out of you in the stoic unit, so that although maybe you missed this today, you kind of can see and go, oh, yeah, I see where that fits. Okay? So I would say the biggest link that kids miss is that this, along with this, gets you that kilojoules per mole, that value. Right? And once you can recognize that information is hidden there for you, it's a lot easier. Does that work? Cool. Okay, third topic. One of the things that you're expected to be able to be fluent in is recognizing different methods of communicating enthalpy change. One of them was actually on the previous slide. Maybe don't get to this one just yet. But being able to recognize that throwing an enthalpy off to the side is a valid method. But I also could have written this as like delta H per mole in the combustion of C2H2, and then I could have said that that number would be 2511 divided by 2, would have been 1255 kilojoules per mole with a negative in front because it's exothermic. And just recognizing all these different methods of communicating. One of the methods that I need you to be able to recognize, and I feel, again, pretty confident that they're going to do this to you, be able to read a graph. This one's pretty straightforward. Here's a graph. Tell me what the delta H is. Take a second to look it over. If you look at the 4 answers, it's not like there's a lot of variety there, is there? 87.1, subtract 74.8. I don't really care which order you do it, but like the difference between those numbers is the 802.3. Right? Like I like to kind of write it from like here to here. In between here is 802.3 kilojoules. So hopefully that narrows it down to 1 or C or D. Now, maybe the more important question then, positive or negative? Yeah, okay, sorry, I didn't catch that. Why negative though? Okay, there's a good one. It's a combustion reaction. All combustion reactions are exothermic. Exothermic is negative. Or maybe another thought is just the reaction is going down. By virtue of it going down, it is losing energy. In terms of losing energy, I mean, granted, okay, energy is not lost, but energy is being released. Energy being released, therefore, is considered to be a negative number. I think this one here is a very simple question, and this is one that's going to save you time, right? Because if you're going to be able to answer a question in 3 minutes or less, hopefully you can look at this one and be pretty comfortable in like a minute or so that you've got it, which saves you some time. If I could point out some distractors they like to do here, what if they gave you a delta H per mole and they threw a little m right here? How would that change things? Well, it depends on what we're talking about. Okay, let's say it was the delta H per mole for CH4. Well, you would have this kilojoules per mole, and you would divide by, in this example here, 1 mole. So actually, in this example, it wouldn't change anything at all. But hypothetically, let's say it was this equation back here, and there was a 2 sitting in front of it there. Well, then you would need to take that number and divide by 2. Does that make sense? Okay, why don't I show you the next question and let you give it a try without me even introducing it. This was our 4th topic. Actually, no, it wasn't. This is our 5th topic. I'm actually out of order today. While you're reading this over and kind of looking at this, I would also say this is another must-have question. Like, they're probably going to ask you one of these. And as you look at it, you might get really frustrated going, okay, clearly I have to have a numerical answer. Right? I mean, it's numeric response. Where the heck are the numbers coming from? And some of you, I think, are picking up on this. You have a data booklet. Don't forget about your data booklet. I don't know that you need to solve this question, but if you were to write out an equation, methane would be CH4 and be breaking up into carbon and hydrogen, which means you'd have a reaction that looks roughly like this. And just so that I'm not a hypocrite, I'll actually throw states of matter in here. There's an equation. Standard numbers are in our data booklet. So as long as you remember how to use your data booklet and how to apply this properly, you just need to look some numbers up. So find methane's number. Methane is negative 74.6. But right here, this guy's on the wrong side, so I'm going to make it positive 74.6. I guess if you wanted to, you could try to look for carbon and hydrogen, but why can't you find them? Or elements. How do you form an element from stuff? I guess if you're talking on the subatomic level, there's protons, neutrons, electrons, but really these guys right here, they don't even have numbers because they're not compounds. So last step then, you just need to add it all up. So your answer, by the way, was 74.6. That was it. Maybe another way of looking at it is this table right here is all about forming things. That question there asks you to decompose something. Is it decomposing the opposite of formation? So just find the number for formation and flip the positive negative sign. So rather than negative, it's now positive. That question right there, when I look statistically at how the province does, is often atrocious in terms of how well students do on that. And I feel like it's because kids get so used to having to do big calculations based on looking for values based on like the preamble they give you. Like, I guess what I mean is they give you one of these little stories where there's like, use the following information. They give you a little story, maybe a picture. You get so distracted looking for that information that they give you a simple question like this and say, all they're really asking you is, do you understand the look and number up in your data booklet? You know what I mean? And it's almost too simple that you kind of psych yourself out and forget about doing something that simple. So don't forget about that concept, because that's another one of those like must-have. Like they're gonna test you on that. Okay, last topic we talked about was something called Hess's Law. The basics of Hess's Law are really, I like a math analogy. If I give you x plus y turns into 3 and x minus y turns into 4, if you did like elimination, you could say that those subtract, that turns into 2y, that turns into -1. It's kind of like a system of equations, only in chemistry it's a little different. Rather than stacking things on top of each other, we're looking for something like a plus b turns into c, and then d turns into a plus e. And you go, okay, well those a's can cancel, leaving you with d plus b turning into c plus e. Does that concept make sense? Ultimately, this is kind of like a fancy, I don't know, it's almost like jury rigging kind of a way where it's like you have to manipulate and kind of piece together an equation that you might not be able to actually solve the equation on its own, but if you solve other equations and fit them together, maybe you can get the answer you're looking for. So you can almost always count again on getting one question like that. So here's one, give it a try. This is Hess's Law. I would say the Hess's Law questions, this one's a bit of a simpler one, but Hess's Law questions are sometimes the ones where you're going to need to spend 3 minutes on, because you're going to have to write out some reactions, you're going to have to flip them backwards or forwards or times them by 2 or 3. This one is not quite that long. Well, hopefully you have some process that you use for Hess's Law that looks like this. And this is just mine, but find your own way of making it work. I look at the final reaction and say I need to have some nitrogen monoxide. The only equation up here that has nitrogen monoxide is the first one, but the nitrogen monoxide is on the wrong side. So I'll just flip the equation. I'll write it as NO turns into half an oxygen plus half a nitrogen. And this 90.2, I'll just make it a negative 90.2. Now this thing's in the right spot. I might not work with oxygen next just because it's in both reactions. I need to have a nitrogen dioxide sitting on the product side. This is the only guy that can have nitrogen dioxide. It's already in the right spot, so I'll just write out the equation as written. Half a nitrogen plus a full oxygen makes that nitrogen dioxide. That puts this guy in the right spot. So I need to keep that as 33.2 in the positives because I didn't change the equation. And if you do Hess's Law properly, everything should cancel. There should be a 2 there. Half a nitrogen cancels half a nitrogen. There's a full oxygen on your reactant side. There's half an oxygen on your product side. So shouldn't that leave you with half an oxygen? So last step, just take these two numbers and add them together. So negative 90.2, and add 33.2, and I get negative 57. And if you wrote that down, you're wrong. Why? Sig digs. You need to have a 0.0. Yeah, don't screw up sig digs. Okay. On your diploma, there are 16 numeric response questions. There's a lot of numeric responses. The worst thing you can do is get one of them wrong because you screw up a sig dig, especially on something so simple. So make sure you're super careful on those. I would say most of the time, in chemistry at least, you know how they give you 4 different boxes? Most of the time, all 4 boxes get used. And that's not a hard and fast rule. Like, there's no rationale I have against that. That's just my experience. Is most of the time things require 3 sig digs. And if they require 3 sig digs, it could be like 47.1 or 1.36. Okay, but they might do this and tell you to do 3 digits. So if they do that, make sure you're careful, but please don't screw up a sig dig on something like this because that'd be bad. Okay, questions, comments, concerns, conundrums, all those other C words. How do you guys feel? Is this refresh your memories? Okay. Tomorrow we're going to write a quiz then. Basically, the way I try to structure my quizzes, if I've never mentioned this to you guys before, your diploma is 3 hours and 60 questions. So we get half that time frame. So I'm going to give you guys an hour and a half, and you'll have 30 questions to do. Okay. I'll give you more time if you want. So like same drill as in the past. If you need more time, you can throw your test in the extra test folder. But you need to start making that a little bit more of on the forefront of your mind. Is like if you're taking an extra half hour every single test, you got to speed up, right? For whatever it is that you can try to get faster at. That makes sense. Okay, cool. Why don't I do the lesson and then give you guys a break? The lesson today is not that long, so why don't we just hop right into that lesson and then we can have some time to work. Okay. Before I start talking about my notes here, maybe I'm just gonna kind of talk off the cuff just about the state of how matter works. Okay. Sometimes I use these little guys here to represent molecules of some kind, but just for the sake of argument today, here, this is solid matter. Okay. Let's say that I want to cause this thing to react chemically. Maybe even the chemical reaction I want to do is a decomposition reaction. Right? Decomposition means you take a compound and break it up into its elements. And if you guys look at your data booklets, the formation numbers right here, hopefully you'd agree as you look through here that most of the formation numbers are negative. Let me say that one more time. If you look in your data booklets here, most of the formation numbers are negative. What would that mean the decomposition numbers are? Okay, and what does positive mean? It means it's endothermic, meaning that it requires energy. And I think that's very logical, because let me go back to my eraser here. Let's go back to this eraser here. Okay. Will this thing naturally decompose? I would say no. That would actually be a horrible thing if naturally stuff just decomposed on its own. Most things, in order for them to decompose, you have to input some energy for the reaction to get started. Does that make sense logically? No, otherwise, I think our world would be in huge trouble. All of a sudden, my chair would just decompose in front of me, right? Like, I mean, it feels like a science fiction sort of thing, like a Star Trek ray, where you aim at them and the molecules just fall apart, right? But like, hopefully that makes sense. That in order for something to break into pieces, and this is the really important thing. In order for something to break into pieces, you need to input some energy for that to happen. Does that make sense? Otherwise, bonds would just start randomly breaking. And that's what my first slide here basically says. When you've got two entities that are going to move apart, it requires energy to break bonds. I think intuitively that makes sense to everybody. Otherwise, bonds would just start breaking in front of us all over the place, and our world would just start collapsing into a whole bunch of elements instead. Does that make sense? The second half then is maybe a little less intuitive, but hopefully it makes sense logically based on the first premise. If when you break a bond, it requires energy. When you make a new bond, it then is going to release energy. Does that make sense? So one more time from the top. Intuitively, hopefully it makes sense that stuff would decompose in front of us just randomly unless it took energy to break a bond. So therefore, to break bonds requires energy. So therefore, when you make new bonds, it's going to release energy. It's going to be giving back energy. Okay? And that's what I want to focus on today is, well, what happens when bonds are formed? Okay? Now, you can take entire classes talking about the moment in time when bonds get broken and remade. We're not talking like seconds. We're talking less than nanoseconds that it takes for a bond to rip apart and reform again together new. Does that make sense? Like this is, again, if some of you were in my physics class, we talked about the quantum world a little bit. You guys remember that terminology? I guess there's only a few of you here who were in that class. But the idea that, things can exist in more than one state simultaneously. A lot of theories that we have based on how bonds break, we don't actually really know what's happening. We know what happens beforehand, and we know what happens afterwards. But for that split microsecond in time where stuff rips apart and goes back together, it takes me a few seconds to do that, right? Well, in a chemical reaction, it happens. Does that make sense what I'm getting at here? Okay. So I guess the point I got sidetracked on is you can take entire courses talking about it. It's called chemical kinetics. If you've ever taken a course on that, where basically it discusses the how and the why the actual chemicals do break bonds and remake bonds, what that looks like, at least what we think it looks like. Here's just a quick slide reviewing what we already knew. If it's an exo and endothermic reaction, positive versus negative in terms of delta H, but I want to focus on the bonds instead. If you have an endothermic reaction, actually, let's get some breakfast. Anybody want food? In this class. Everybody? All right. Thanks, guys.
That's it?
I think so.
Wow.
I know, we don't eat food in this class.
Oh, come on.
Okay, so let me go back here about breaking and making bonds. Let's say you have a combustion reaction that's clearly exothermic, because combustion's exothermic, right? In order for the reaction to get started, first you have to break some bonds, and then you have to remake new stuff. Does that make sense? Well, if something is exothermic, it must require more, let's do this one here first, exothermic. It must take less energy to break bonds than the energy you get back when you're done. Like, let's just put some numbers to it. Let's say it takes 5 kilojoules to break the bonds. But then when you re-put new bonds back together, you get back 10 kilojoules. Well, start with 5, but then get back 10. If you think of it like a business, maybe in a way, your startup costs are 5, but then your revenue is 10, so you've made a grand total of 5, so then it's exothermic. That makes sense? Whereas in an endothermic reaction, in order to break the bonds, it's actually more than you get back when you're done. So in like a business world, that would be like your startup costs are $10, and then you only make back 5. Did you actually make money at the end of the day? I'd say, well, no, I guess not. If you put in $10 to start with, and then you made back 5, you actually you kind of put in 5 by the time you're done. Does that concept make sense? Okay, here's where we're going to diverge into a bunch of graphs, hopefully. And I need to do one of those apologizing things I do once in a while, where I've been telling you half-truths for a while, just to make things simple. A lot of the graphs that I've been showing you are not probably the most accurate description of what's going on. Sometimes you will get graphs that look like this guy right here. But from now on, we're going to change the way our graphs look into something more like this. So we'll start with this one first. This is all one reaction still. Okay? So there's not multiple reactions happening. What we've got going on here is, here we've got some hydrogen and some chlorine molecules. And you guys can see that there is a bond illustrated between them. In order to break bonds, it requires energy. Therefore, the graph is then going to go up, because you need energy to break a bond. At this moment right here, there are no bonds between atoms. For like a nanosecond, even smaller than a nanosecond, no bonds exist. We actually have a name for this. And I know it's on further slides, but we should point it out here. It's called the activated complex. Basically, it's a millisecond, nanosecond in time where no bonds exist. All of the molecules have broken their bonds. Well, then they rearrange themselves. So rather than hydrogen bonding with hydrogen and chlorine bonding with chlorine, hydrogen bonds with chlorine and hydrogen bonds with chlorine. They rearrange themselves. for whatever reason and in whatever sort of geometry it requires, but they find a way to rearrange themselves, and they make new bonds. Well, if breaking bonds requires energy, hence the going up, making bonds is going to give back energy. In this particular example, it's an exothermic reaction then, because the amount of energy required to break the bonds, whatever that number was, is not as much as the energy given back when new bonds were made. And so therefore it's a negative delta H, because this number is smaller than this number. Does that make sense? This is probably a better representation of a graph. I guess the biggest problem though is that along this axis here, you might see the term reaction coordinate. I think that's probably the most appropriate term to use. Sometimes people use the word time, but time is probably not appropriate because the length of time that this is and the length of time that this is not the length of time of the activated complex. The activated complex is basically, well, faster than that. Does that make sense? So sometimes rather than using time, we'll use this terminology instead. Basically just describing what's happening to your reaction. Let me just walk you through some more pictures because that's most of what's happening today. You know what? Let me skip the word slides and let's just look at the other picture ones here. Let me go to this one here. You can find that one. Probably the more typical thing that you'll see as a graph is rather than it being line up, over, line back down, kind of like that first picture, it might look like this graph right here. This is a very typical graph picture that you'll get now. Where, actually, let me start by asking you guys this question. Do you think this is an exo or endothermic reaction? It is exo. Why is it exothermic? Ultimately, it goes down, yeah. This right here to this right here has a net loss of energy. However, in order for the reaction to proceed, you kind of have to put in some energy to start with to get the reaction going, and then after that, the reaction kind of falls down. The analogy this graph has is like of a ball rolling up a hill. The ball is ultimately going to go from the top of a hill down to the bottom of the hill, but first it has to kind of go over the crest. And so in doing so, it's going to take you some energy to get the ball over the top of the hill. And then once it does that, it's going to roll down to at least where it started with and possibly even further past that point. Does that make sense? Okay. All reactions then have this term. It's called an activation energy. It's the amount of energy required to get the reaction started, to get the ball rolling, if that analogy makes sense. In a combustion reaction, what is the activation energy that gets the reaction going? Do you guys know? Okay, what's a combustion reaction? You're blowing something up, right? How do your car, for example, this morning, needs to blow up octane, gasoline. How does it start blowing up though? What does your car have inside of it that gets it started? The ignition, which is made of a spark plug. Does that make sense? A spark gets the reaction going. It gives it that initial little bit of energy to get started, and then gives off a lot of energy. Does that make sense? Maybe I skipped that in the word slides. Let me see if I can find that information here. Here we go. The initiation energy would be like a spark. Okay. There are some reactions that just spontaneously happen. But if I can go back to the initial thing I talked about, wouldn't it be a horrible world if just all things just randomly started reacting for no reason? Like, that'd be horrible, right? So this is actually very good for our society that things actually have this required activation energy to get going, where before you start, you have to at least put in some energy before the reaction keeps going. By the way, an endothermic graph would look something like this. But either way, you have to have this initial input to get the reaction going, lighting a match. So sometimes all that's required actually is just the basic room temperature of the room. Okay? Fortunately, most reactions don't react just at room temperature just like that. I mean, like I said, if my board just started falling apart randomly due to room temperature, that'd be a problem. But what might happen if I heated this thing to 1,000,000 Kelvin? Yeah, then it might react. Does that make sense? So, okay, maybe that was a bit extreme. Okay. Another thing we should talk about here is this word that I skipped over here. In order for reactions to occur, there have to actually be physical collisions. Can this atom over here and this atom over here, can they react with each other if they stay apart from each other? wouldn't it make intuitive sense that at the very least they have to hit each other? That they have to actually come into physical contact with each other for a reaction to occur. So I like to think of it from a physics point of view as like a momentum kind of collision where here's A and here's B, and they have to smash into each other. Does that make sense? And if they smash into each other with enough energy, they might be able to rearrange themselves and make something new. But if these guys kind of react with each other like this, they might just bounce off each other and nothing would happen. Does that make sense? So that's that activation energy, or right down here, I guess, sufficient energy. There has to be at least enough to get the reaction going. A spark of some kind. Okay. I doubt you'll get tested on this, but I want you to know this anyways. You also have to have the right positioning. Okay. Imagine that you have, I don't know, let me just make some really quick molecules here. Let's say you have, you can see these relatively well from where you're at. Let's say they collide in this orientation like this. That might not work, but that might. Does that make sense? So like sometimes you have to have the right three-dimensional geometry. If they try to collide like this, it might not work. Maybe because this guy right here is a hydrogen and this guy right here is an oxygen, and so maybe that doesn't work. But if it flips around and this guy right here happens to hit that one right there, well, now maybe the reaction can occur. Does that make sense? So the two basic things you have to have is they have to smash into each other with at least enough energy to get going, and that depends on the reaction type. But they also have to have the right geometry. I think that's what this slide right here has, where you've got these two guys right here. They're going to slam into each other. So long as they have the right energy and orientation, for a moment in time, basically everybody's going to be smushed together as one molecule, and bonds will cease to exist. And then they'll find a way to rearrange themselves into something new. All right, let's keep moving on here. So more pictures here of basically the same stuff here. Here you've got some molecules. These molecules on their own don't have enough energy, but if they find a way to slam into each other with enough kinetic energy to get going, and overcome this activation energy barrier, then up at the top here is the activated complex, where bonds are basically breaking and instantly forming new ones. And then as the energy drops back down, it ends up being exothermic. Does this make sense? Am I kind of repeating myself now a lot? Cool, you're not. I'm going to move on then. Side note, you guys ever heard of the Hindenburg? Yeah, pretty much. They decided to make a blimp using hydrogen, which, yeah, I mean, yeah, it's not a bad idea, I guess. I mean, hydrogen is lighter than air, so it should float. Only problem is it's flammable. Well, it's actually not a problem unless there's a spark, and I mean enough of a spark. But once it gets going, it's pretty much like a chain reaction that you can't stop, right? So I mean, even just a little spark, maybe not the biggest problem in the world, but as soon as that activation energy barrier had been met, all of a sudden it became vastly exothermic and released a whole bunch of energy to the point where the whole thing basically combusted, right? So, here's a picture of an endothermic reaction. Exo, I think, is a good place to start, but here's endothermic. Hydrogen and iodide, you need to put in a lot of energy to get it going. And then as it re-releases that energy as bonds are formed, you'll notice here that it's not as high as it was before. It's actually, well, it's not lower, now it's higher. So this is what an endothermic graph might look like, where it actually requires a lot of activation energy to get going. And not only that, but you don't even get back what you put in. Does that make sense? A side note I want to mention here, sometimes you might get asked about the activation energy for the reverse reaction. If going this way is the normal reaction, going this way would be the reverse reaction. What would the activation energy of the reverse reaction then be? That would be the activation energy for the reverse reaction. Does that make sense? So if you wanted to put this reaction in reverse, going forward it's exothermic, but going backwards it's now, I said that wrong. Going forward it's endothermic, going backwards would be exothermic. Does that concept make sense? Long story short, you're probably going to get a graph, okay? And they might give you a graph like this one I showed you back here. Oop, too far. Like that. They could give you a graph like that, but I've also seen them give graphs where they draw them more like this, and they'll put a number on here like say 100, 150, 200. They might even throw negatives on there. Don't let that freak you out. And they might ask you, like, what is the activation energy for the reverse reaction? Want to take a stab at it? Based on this picture right here, what's the activation energy for the reverse reaction? Positive 100. So the forward reaction would be going. So that's not what we want. For the reverse reaction, that would be starting here. How much do you need to get over top of the hill going the other way? Well, you'd have to go from 100 all the way up to 200. So the activation energy for the reverse reaction would be positive 100 in order to get up over that hill. Does that make sense? What if I asked you what the enthalpy change was for the forward reaction? What would that be? Negative 50 is correct. Because for the forward reaction, you're starting here, and although yes, you are going up over the hill, where you finish is down here. So your enthalpy, your delta H, would be negative 50 because you start at 150 and go down to 100. That make sense? So chances are you're going to get graphs. I'm going to give you graphs on tomorrow's quiz. Actually, no, sorry, I'm not. This information is not on tomorrow's quiz, by the way, just so you know. Okay, what do I got left? Does that pretty much cover most of my notes? More pictures, basically. More pictures. Hopefully I've covered that. Do you guys have questions? Quick summary then. I kind of lied. Hopefully you guys get why I do that though. Like I told you a partial truth. The graphs that I've been showing you, not really the best graphs you can have, although they work. You're probably going to get a graph that looks more like this. In order for a reaction to occur, you need to break the energy barrier called the activation energy. You need to input some energy to begin with. To break bonds requires energy. For then a split moment in time, there won't be any bonds. That's called the activated complex. It's the peak, the crest of that graph. And then you're going to re-release some energy. Depending on whether you release more or less energy than you started with, makes it endo or exothermic. So breaking bonds requires energy. Making bonds gives off energy. By the way, what form of energy would it need to be in order to break those bonds? What form of energy would you need to have in order to break the bonds? What did you say? Good, kinetic is the right answer, yeah. Does that make sense? In order to break bonds, this molecule and this molecule must have enough kinetic speed so that when they collide into each other, they can actually rearrange. Does that make sense? So that's the form of energy required to get going. You need kinetic energy to get the thing started so that potential energies can eventually change afterwards. You good? Cool. Go take a break, and then when you come back, either finish up anything you're not done, or start getting ready for tomorrow's quiz.